Greetings, students. Today we delve into a fascinating challenge presented by LeetCode, specifically Problem 206, Reverse Linked List. This problem invites us to explore the elegant structure of singly linked lists, a fundamental concept in computer science. At its core, we are tasked with reversing a linked list, a sequence of nodes where each node seamlessly connects to the next. Imagine a list that begins with the node containing the value 1 and concludes with 5, represented as 1, 2, 3, 4, 5. Our objective is to rearrange this structure such that the last node now leads the list, followed by 4 and so forth, resulting in 5 and 4, 3, 2, 1. As we embark on this intellectual journey, I encourage you to consider the implications of this reversal and how it showcases the dynamic nature of linked lists. Let us proceed to unravel the intricacies of this problem together. Linked list traversal is the process of visiting each node in a linked list, starting from the head, or the first node, and moving through to the end of the list. A linked list is made up of nodes, where each node contains a value and a reference, or pointer, to the next node. This structure is particularly useful because it allows for efficient insertion and deletion of elements. To access or manipulate data in a linked list, you need to traverse it, since the nodes are not stored contiguously in memory like they are in an array. Understanding traversal is vital because it supports many key operations in computer science, such as searching for values or counting nodes. In simple terms, traversal is like following a chain. You start at the head, and you follow the pointers from one node to the next until you reach a node that points to null, signaling the end of the list. During this journey, you can perform various operations on each node, such as printing its value or modifying it. Mastering this technique lays the groundwork for more complex algorithms and data manipulations you'll encounter later. In this example, we are looking at how to reverse a linked list using traversal. First, we define a node class, which is the basic building block of our linked list. Each node has a value that stores data and a next pointer, which is initially set to none. Next, we have the linked list class. It starts with a head that points to the first node. When we append a value, we create a new node and either set it as the head if the list is empty, or traverse to the end of the list to link it there. The traverse method walks through the list, starting from the head. It collects the values of each node by following the next pointers until it reaches the end. This process gives us a complete view of all the values stored within the linked list. In our example usage, we create a linked list, append values 1, 2, and 3, and then use traverse to get and display these values. Understanding this traversal is key, especially when we later explore how to reverse the order of the nodes. Pointer manipulation refers to the techniques involved in managing pointers, which are variables that store memory addresses of other variables. In programming languages like C and C++, pointers are vital for accessing and manipulating memory directly. This direct access allows programmers to efficiently manage memory and create complex data structures, such as linked lists and trees. The real power of pointer manipulation lies in optimizing performance and memory usage. By using pointers, developers can create dynamic data structures that adjust in size during program execution, which is essential for effective resource management. This capability is particularly important in high-performance scenarios like systems programming, game development, and real-time applications. At its core, pointer manipulation includes key operations such as dereferencing, accessing the value at a pointer's address, and pointer arithmetic, which allows for navigation through arrays and data structures. Pointers can also be reassigned to different memory locations, providing flexibility in data handling. Mastering these concepts is crucial for understanding memory management and data structures in advanced programming. In this example, we're looking at a function called double elements, which takes an input list, R, and doubles each of its elements. First, we initialize an empty list named result, where we'll store our doubled values. This is like setting up a clean workspace before you start a project. Next, we iterate over each element of the input list using a for loop. Think of this as going through a stack of cards one by one. For each card, or in this case, each element, we multiply it by 2 and add that new value to our result list. Finally, we return the result list, which now contains all the original numbers doubled. This process highlights how we can manipulate pointers in a list to create new values without altering the original data. Understanding this is crucial for more complex operations in data structures. LeetCode problem 206 involves reversing a singly linked list, a fundamental concept in data structures. To tackle this, first we need to understand that reversing means the first node will become the last, and the second will become the second to last, and so forth. We start by defining our data structure. Each node in a singly linked list has a value and a pointer to the next node. Next, we initialize 3 pointers. Prev will be set to none since the new tail will point there, and current starts at the head of the list, where our processing begins. As we iterate through the list using a while loop, we store the next node, reverse the link of the current node to point to prev, and then move both prev and current one step forward. This process continues until we reach the end of the list. After the loop, prev will point to the new head of the reversed list, which we then return. This algorithm runs in linear time, ON, and uses constant space, O1, making it efficient for this task. In the provided Python code, we define a list node class and implement the reverse list function to demonstrate these steps programmatically. This approach not only reinforces our understanding, but also illustrates the elegant simplicity of linked list manipulation. Today, we will explore LeetCode problem 206, which challenges us to reverse a singly linked list. The task requires us to manipulate the list in place, meaning we cannot allocate additional space for another list. Key constraints include the length of the list, which ranges from 0 to 5,000 nodes, and the values of the nodes, which must lie between -5,000 and +5,000. These parameters are critical as we devise an efficient solution. The provided Python code addresses LeetCode problem 206, which involves reversing a singly linked list. This solution uses an iterative approach, which is both efficient and straightforward. At the core of this implementation is the list node class, which represents a node in the linked list. Each node has a val attribute for storing its data and a next attribute that points to the next node in the sequence, allowing us to traverse through the list. The reverse list function starts with 2 pointers, prev, set to none, and current, pointing to the head of the list. Using a while loop, we continue iterating until current is none. Inside the loop, we temporarily save the next node in next node to avoid losing access when we reverse the next pointer of the current node to point to prev. This reverses the direction of the nodes. After adjusting the pointers, we move prev to current and current to next node, effectively moving through the list. When the loop ends, prev will point to the new head of the reversed list, which we return. This method is efficient, with a linear time complexity of ON and a constant space complexity of O1. The iterative approach minimizes overhead compared to recursive methods, which could risk a stack overflow for large lists. Understanding these concepts will help you grasp fundamental data structure manipulations effectively. The time complexity for reversing a linked list is ON. This means that if you have n nodes in your list, you will need to visit each one exactly once to reverse the pointers. Think of it like flipping through the pages of a book. You have to go through each page to see the entire story, which is what we do here with each node. Now, let's look at the space complexity, which is O1. This indicates that we are not using any extra space that grows with the size of the input. Instead, we are performing the reversal in place, meaning we only need a fixed amount of space regardless of how many nodes there are. It's like rearranging books on a shelf without needing additional shelves. By understanding these complexities, you can see how efficient the reversal process is while using minimal resources. This efficiency is crucial in programming, especially when dealing with large datasets.